This is section 9.3, answering questions about the mean of a population. Let's start with a review of what the sampling distribution is. It's a probability distribution for statistics. In this chapter, we're interested in X bar. It shows us all the possible values of the statistic on the horizontal axes. It gives us the probability of each possible statistic, that is, how often we can expect to see a particular value of our estimator. It gives us important characteristics of the estimator, such as bias, precision, and it allows us to quantify how far off our estimate is likely to be by calculating the probability that an estimate falls a specified distance from the population value. And finally, it is used for making inferences about a population. It allows us to generalize the results of a survey, our sample of a survey, which is our sample, to a larger group, the population. So let's look at an example, number 2. Imagine a large population, such as all iPad batteries in the US. Let's assume that these iPads have 10-hour battery life, give or take 3 hours. Suppose we take a simple random sample of 25 iPads and calculate the average battery life. Let's first see, can we use the central limit theorem to create the sampling distribution for X bar, the average battery life for a random sample of 25 iPads. So the first thing we need to do is to check the 3 conditions to use the central limit theorem. The first condition, the sample is collected randomly from a population, and the observations are independent of each other. So looking back at our original question up here, imagine a large population. Let's assume that these iPads have battery life, give or take, blah, blah, blah. Okay, so suppose we take a simple random sample. So this is met, check. And the fact that we're taking a simple random sample of 25 iPads, they're definitely going to be independent of one another. So the next, the sample size N is large enough unless the population is normally distributed. So we don't know anything about the population, but our sample size N in this case is equal to 25, and that is the cutoff. If N is greater than or equal to 25, we say it is large enough. So that condition is also met. And condition number 3, if the sample is collected without replacement, then the population size must be at least 10 times bigger than the sample size. Well, we have 10 times our sample size, which is 25, is 250. And this is definitely less than the total number of iPads. So this is also met. So all 3 of our conditions have been met, which means we can use the central limit theorem to create a sampling distribution for X bar. So that means that we expect that our X bar is going to be normally distributed, and it's going to be centered at our mean mu, which is 10, and our standard deviation is going to be, our standard error is going to be 3 divided by the square root of our sample size, which is 25, and that is equal to 0.6. So now we know what our sampling distribution looks like. It's normal, it's centered at 10, and it has a standard error of 0.6. So this would be, and we can fill out our distribution. According to this sampling distribution, what should we expect the average battery life of our sample to be? Well, we'd expect it to be about 10 hours. Give or take 0.6 hours. What is the probability that the sample mean will fall within 2 standard errors of the population mean, mu? So we expect that our sample mean will fall within the population within 2 standard errors of the population mean about 95% of the time. Our conclusion that we should expect our sample mean to be 10 hours, give or take 0.6 hours, is useful because it implies that in general, we can predict where X bar will fall relative to mu. It indicates that X bar is very likely to fall within 2 standard errors of the true value of mu, as long as the sample size is large enough. If we have a small standard error, then we know that X bar is quite likely to fall very close to mu. If we can predict that X bar will fall close to mu, then we can also predict that mu will be close to the sample proportion X bar. Let's return to the more realistic situation of not knowing the value of mu. Typically, we wouldn't know the value of mu, and that is why we'd be doing the study. So let's have a simple random sample of 100 GCC students. It has the mean of 68 inches and a standard deviation of 4 inches. Note, in this case, we have access to sample data, but not the entire population. This means we're actually calculating our X bar, but we do not know mu. So what is our X bar? Our X bar is 68 inches. Is this estimate biased or estimate unbiased? Yes, and that is because we saw that it had simple random sampling and independent observations. So we can assume that it is an unbiased estimate of mu. Estimate the standard error. Our standard error is going to be equal to the standard deviation of our sample, which we saw is 4 inches. So 4 over our square root of our sample size, and that is 100. That comes out to be 0.4. What does the standard error tell us? That X bar will be near mu, plus or minus 0.4 inches. What do we know about the sampling distribution for X bar? So are our CLT conditions met? So we have 1, we said that there was simple random sampling and independence. 2, is n large enough, and n is greater than or equal to 25, so that's met. And 3, our population size will be bigger than 100 times 10, which is true. So there's more GCC students than 1,000. So what does the sampling distribution for X bar look like? Well, the sampling distribution for X bar is going to be centered at mu, and it's going to be mu plus 0.4, mu plus 0.8, mu plus 1.2, and then the same on the other side, mu minus 0.4, mu minus 0.8, and mu minus 1.2. What else can we conclude about this? Since it's highly unlikely that X bar is more than 3 standard errors from the population mean mu, it's also unlikely that mu is more than 3 standard errors from X bar. This means that we can be highly confident that the population parameter mu is between these 2 numbers. So we're pretty sure, we're highly confident that mu is actually between X bar minus 3 standard errors and X bar plus 3 standard errors. In this case, that's 68 minus 1.2, 68 plus 1.2, or simply between 66.8 and 69.2 inches. And this is an example of a confidence interval. This confidence interval could be reported in the following form: 68 plus or minus 1.2 inches. And just as in chapter 7, where you already saw confidence intervals, we know that they report the sample mean plus or minus some amount. This some amount is called our margin of error, which tells us how far from the population value our estimate is likely to be. A confidence interval provides two pieces of information: a range of plausible values for our population parameter mu, and a confidence level, which expresses our level of confidence in the interval. They're calculated as follows. So we have X bar plus or minus our margin of error. The margin of error is some multiplier times our standard error. So we just select our margin of error based on our desired confidence level. The following diagram shows 4 different margin of errors for a sample in which X bar equaled 68 inches and our standard error was 0.4. So here we have a low confidence level, 68%, but we get this very narrow confidence interval. The confidence interval reported on the other page was 3 standard deviations, and that matches up with a 99.9% confidence interval. So if we want our confidence interval to be our confidence to be pretty high, then we have a little bit wider interval. Let's consider what is meant by a range of possible values for our population parameter mu. By taking another look at our sample of 100 GCC students with a mean height of 68 inches, reminder, in this case, we have access to the sample data and we were able to calculate X bar, but we do not know the population mu. So based on which of the following sampling distributions for X bar, the mean height, which of the following sampling distributions for X bar, the mean height of the sample 100 could have produced an X bar value of 68 inches. So is it likely that if our mean were 66.4, would we be likely to see a X bar of 68 inches? That's somewhere over here, so that's not very likely in this case. Here, 68 inches is here, so if our mean were 66.8, it's possible, but still pretty unlikely. If our true mean were 67.2, and we saw an X bar of 68, then now it's more likely that that could happen. Here, 68 is here. Here, these ones are far more likely sampling distributions to end up with an X bar of 68. And now we're going off kind of on the other extreme. I read that wrong, sorry, 68's here. And over here, 68 doesn't quite make the thing. So again, this is pretty unlikely. So are these the only sampling distributions that our X bar could have come from? And the answer is no. It could have come from any mu between 68.8 and 69.2 would produce a viable sampling distribution where we'd see an X bar of 68. A confidence interval provides us a range of plausible values for our population parameter mu. This means that of all the values in the interval, not just the endpoints, are plausible values for mu. It also means that our sample result, X bar, is plausible result given a sampling distribution for any value of mu within our confidence interval. Let's return to the first scenario where mu was known so that we can get a better sense of what the confidence level means. The following is a normal model for the sampling distribution for X bar, the mean battery life for a random sample of 25 iPads when mu is 10 hours. One student decides to take a random sample of 25 iPads and finds X bar is 10.8 hours. This student calculates a confidence interval using 2 standard errors. Will this capture mu? So their X bar was 10.8 plus or minus 2. We're looking at 2 standard errors of 0.4. And so we get 10.8 plus or minus 0.8, which gives us a confidence interval of 10 and 11.6. So this does actually capture mu. Another student decides to take a random sample of 25 iPads and finds that X bar equals 8.3 hours. This student calculates a confidence interval using 2 standard errors. Will this capture mu? So we have 8.3 plus or minus 2 times 0.4, and this gives us the interval 7.5, 9.1. So this does not capture the true mu, which is 10. So this is the important idea, is that 95% of the time, this process will capture our true mu. So what proportion of the X bars in our sampling distribution will produce a successful confidence interval using 2 standard errors? So we're talking from 8.8 to 11.2, 95% of the intervals will capture the true mu, will work, where 5% of the time this interval won't be capturing mu. So 5% won't work. Out in these tails. So the confidence level tells us how often the estimation method is successful. Our method to take a random sample, calculate X bar, and then calculate the confidence interval to estimate the population proportion. If the method has a 100% confidence interval, the method always works. So then in that case, your confidence interval would be pretty wide. If the method has a 95% confidence level, then the method works 95% of the time for or for 95% of the sample proportions. If the method has a 10% confidence level, it only works 10% of the time, and you'd have a very narrow confidence level or confidence interval. We say the method works if the interval captures the true value of the population parameter. In other words, the interval works if the true population mean is inside the interval. Remember, the population mean is, keep in mind, the population mean does not move. The population mean is some set number. We just don't know what it is. It's our interval that we calculate that really moves around it. However, the confidence interval does change every sample we collect. Thus, the confidence level measures the success rate of the method, but not of one particular interval. How do we choose a level of confidence? This process is similar to the process used in Chapter 7. The more confident we want to be in our interval, the more standard errors we should use. So we'd have a wider interval. But we will be using the t distribution, so this is a little bit of a change, rather than the standard normal distribution to find our multiplier. So the formula for a confidence interval is X bar plus or minus your margin of error. M is your margin of error. Okay. So how do we calculate our margin of error? Our margin of error is our standard error estimate times T star. And T star is a special multiplier that's chosen to achieve our desired level of confidence. We'll get into this more on our next page. Remember, this formula depends that the CLT conditions are met. And so we always have to check those first. The multiplier T star is a constant that we use to fine tune the margin of error. So it has the level of confidence we want. So it's similar to what you saw when we were using Z star. But now we're going to be using a T distribution. So we use the T distribution with n minus 1, where n is our sample size, and we call this n minus 1 degrees of freedom to find our multiplier. The degrees of freedom determine the shape of the t-distribution. As the degrees of freedom increase, the t-distribution gets closer to the normal distribution. So the t-distribution has slightly thicker tails. So when your degrees of freedom are 1, okay, so that's a really small sample size. I'm highlighting the t-distribution in red. You can see that the tails are thicker than the tails of the normal distribution. But as your degrees of freedom increase or your sample size increases, your the tails of your t-distribution get closer and closer to the normal. And when your sample size is larger and your degrees of freedom are larger, it's basically a perfectly like our normal distribution. Okay, so the t-distribution is another distribution. It's similar to the normal distribution. It's symmetric, mound-shaped, and unimodal. We find that it's a better distribution to use when you have a smaller sample size because it takes in more uncertainty in the tails. The t-distribution has thicker tails than the standard normal distribution, and these tails get thinner as the degrees of freedom increase. Thicker tails indicate that extreme values are more likely. Why do we use the t-distribution rather than the standard normal distribution? It is because we are using an estimated standard error rather than the standard error itself. The estimated standard error uses S, the sample standard error, in place of sigma. And although it's unbiased, there's potential that this estimate is not as close as we would like, especially in smaller sample sizes. Using the t-distribution to get our multiplier makes up for this uncertainty. So it allows for slightly more extreme values because we have a little bit more uncertainty. The next page contains a copy of the t-distribution from the back of your textbook. Look at the column for 95% confidence level. What happens to the t-distribution what happens to t star as the degrees of freedom increase? So here is our t-distribution table, and we're focusing on the 95% column. And as this is our t star is inside of here. So with 1 degree of freedom, we're looking at 12.706. But as our degrees of freedom increases, which is the same thing as noting that our sample size is increasing, and we get all the way towards the bottom of the table, which I can't fit on one page, we end up at 1.960. And this is the same thing as a 95% confidence interval with Z star. So if we have a really big population, these T star values equal our Z star values, okay? So just showing further that when your sample size is really big, T and Z are not very different from each other. So how do we interpret a confidence interval? Let's use a confidence interval we've already calculated. The 99.7 confidence interval for the mean height of GCC students was 6.8 inches to 69.2 inches. This confidence interval tells us that any value between 66.8 and 69.2 is a plausible value for the mean height of all GCC students. Any value outside the confidence interval is not plausible for the mean height of all GCC students. It's not impossible that the population value is outside the confidence interval, but it would be very surprising. Also, we can interpret this confidence interval as follows. We can be 99.7% confident that the mean height for all GCC students is between 66.8 inches and 69.2 inches. If we were to repeat this survey many times, then the 99.7% of the surveys, if we were to repeat this survey many times, then in 99.7% of the surveys, the resulting confidence interval would succeed in capturing the mean, would succeed in capturing the mean height for all GCC students. So two different ways of interpreting it. Remember, our confidence interval, our confidence is in our process that produces our interval, not in one particular interval. We never know if that one interval that we produced actually captures the mean. We just have a confidence of 95% or 99.7% that the mean would be in that interval. It's incorrect to say that a particular confidence interval has a 95% chance of including the true population. In other words, we don't want to use the word chance or probability. Instead, we say the process that produces confidence intervals captures the true population parameter with 95% probability. So notice now we're talking about the process that creates the interval.